rapid advances in technology, the ability to work virtually in 3D is now common. Today, we will be exploring two very distinct environments that utilize 3D technology. We'll start with industrial automation. Factories are generally very dense with equipment, people, and machinery. A traditional 2D layout will only depict a single layer, usually on the shop floor. Cable trays, conveyors, and piping systems will frequently go undetected in these plans, making clash detection difficult to impossible. These interferences will result in field change orders, project delays, and cost overruns. A true 3D as-built condition is required for efficient collaboration and project control. Because of the complexity of industrial automation, 3D technology has been utilized for over 15 years. The demands of shorter cycle times required planning, modeling, and simulation for verification before any work was done at the plant. It was imperative to have an accurate as-built model of the plant in order to utilize the new digital technologies. Probably the greatest impact of 3D factory technology has been reduction in construction times. All design and validation can be done digitally with assurance of accuracy before the plant is scheduled for shutdown maintenance. This also results in reduction or elimination of field change orders, greater project control, and collaboration. Going forward, the plant will have a complete asset database of all equipment installed on the shop floor. Instead of spending hours manually sketching out factory assets, you can now get them for free from ever-increasing libraries of parametric factory objects. Factory design software now includes a wide range of smart objects such as conveyors, material handling equipment, robots, electrical equipment, and families content. And it makes it easy to resize and edit assets based on your layout requirements. 3D Factory enables you to create compelling 3D visual fly-throughs and walkthroughs of your machine layouts and share it with your clients and non-technical stakeholders. This not only enables you to clearly communicate your layout ideas in 3D, but also helps you to differentiate over someone who is communicating layout ideas in 2D. Identify any potential problems before equipment is installed or commissioned on the factory floor, and still create traditional 2D paper deliverables for your installation team, all from the same source data. 3D Factory delivers extended capabilities for design validation and collaboration. Multi-CAD support will work seamlessly with native CAD data from a wide range of design systems. By aggregating data into a single digital factory model, tools such as visual fly-through and walkthrough can be utilized for visualization and design certainty. Laser scanning can be used to capture as-built state of the facility for clash detection capability, and collaboration tools can be used to easily communicate with suppliers and partners. This chart shows the effect 3D workflows can have on the number of field change orders seen on a typical factory construction project. These numbers are from a series of real projects done with one of the world's largest manufacturers. They show the progression from typical 2D processes to advanced 3D implementations and field orders dropping from over 35% of the total project cost to less than 5% with 3D workflows. During schematic design, models for true as-built conditions can be created in far less time than designed from manual measurements. To visualize proposed changes, new elements can be added to the model to evaluate multiple scenarios. Today, we can easily integrate data from almost any source into a single project coordination model. We can mix point clouds with Revit and native equipment data from suppliers. In 2012, a large automotive manufacturer needed to install the fifth in a series of identical heat treat furnaces. For the 4 previous installations, the decision was made to remove the roof and raise the bottom truss cord by 10 feet. When production needs drove the decision to install the fifth furnace, plans began to raise the roof line once again. PMC was able to scan and work with a structural engineer to design a plan that eliminated the need to raise the roof line of the building. The manufacturer's model was inserted into the point cloud to verify clearances. Using point clouds, fabrication CAD data, we can achieve enough design confidence to enable full off-site fabrication. In 2002, General Motors began using 3D models and laser scanning to quickly update the layouts for the existing general assembly and body shop facilities internationally, quickly adapting the process as a key used in future program modifications. PMC has converted and completed over 6 million square feet of plant floor to functioning 3D models. Using 3D digital engineering, cycle times can be reduced, field change orders eliminated with overall cost reductions. The largest obstacle to 3D Factory is the huge inventory of existing facilities remaining in 2D formats. 3D laser scanning can be used as a segue. This case study is a new weld water line for an automotive plant. The plant layout was in 2D, and the architect designed the new line in 2D. The OEM wasn't convinced of the accuracy against potential clashes due to the density of the MEP in the planned route. PMC's solution was to create a 3D model in Inventor from the 2D drawing and overlay that model into the scan. A series of collisions were detected, including existing piping, fencing, and numerous light fixtures. This study, which was completed in under 2 weeks, saved an estimated $60,000 in field change orders, and more importantly, valuable time lost in new fabrication. I'd now like to move into our second application for 3D technology, Building Information Modeling, or BIM. For greenfield projects, Revit can be utilized out of the box, but renovation or adaptive reuse projects pose a different challenge. The initial step in the workflow is to accurately gather data from the site. As-built plans are rarely accurate or even available, so the first step is to do a 3D laser scan of the building. This is the complete record of the building, including geometry. The process of producing this data is to combine the individual scans during registration and create the point cloud. 2D drawings and elevations or a 3D Revit model can be drawn from this laser scan point cloud. This is a sample of the Revit model created for this project. There will always be the need for 2D drawings, construction and installation documents, for example. This can be done from the same laser scan data. Point clouds cannot carry extended data such as warranties, install dates, or vendor names. Because of this, a scan cannot be directly used as an FM model. We are able to add select model data back into the scanned data and make the new data set integrate into many facility management systems. In this case, the majority of the visible data is from scanning, but the drop ceiling grid originated in the Revit design model. Combining data in this way extends its usefulness further into the building's life cycle. Although point clouds can be integrated into most modern facility management systems, you will almost always need a BIM or Revit model as well. Having the BIM will allow data to be attached to individual objects such as doors, walls, air units, and other fixtures and devices. This is a sample from a Revit model. By clicking on this small window, which is outlined in blue, the properties of that element are displayed in a pop-up window. These include dimensions, manufacturer, finishes, etc. This data can also include asset management information, such as projected replacement date or date last serviced. Once the 3D model is completed by the architect, element data can be incorporated. A virtual mock-up of the materials or takeoff sheets can be created, giving an accurate costing of the project. Additionally, accurately placing the model in the civil site plans before construction in a digital model can identify incorrect or missing parts of the model. If proper modeling guidelines are followed when creating the BIM, the geometry and data will easily import into most digital facility management systems. Once the source data has been completed, you could usually be up and running in a facility management system in minutes. To get the most out of a digital facility management system, you will need a smart model. Although basic 3D models can work, they will not contain complex relationships, such as tying a light fixture back to its parent electrical panel. Once the geometry and data have been added to the CAD model, the data must be exchanged to the facility management system. This exchange happens through the use of COBie for data and IFC for geometry formats. These formats are widely supported within both the CAD and facility management system industries. Extended data can include anything that needs to be tracked. Systems are important when analyzing a building. For example, the primary shutoff valve for a specific fixture can be quickly found, or the breaker for a lighting circuit can be identified by just clicking on the light. Modern facility management systems all support dynamic, map-based navigation. This makes finding information easier and also serves as a visual clue to how the system's data is being managed. Because the systems support multiple buildings and even multiple campuses, it becomes easy to get cross-sectional data on all your assets. Want to know the average life left on all the roofs across all of your properties? This and much more are readily available to enable smarter, faster decision-making. The real value of BIM is post-construction. Historically, facility management required numerous systems to collect and manage data. Floor plans, photos, plan elevations, building maintenance schedules, and building automation systems were routinely in separate sources and often in separate departments. With the introduction of BIM, owners and facility managers can optimize the way that buildings are designed, built, managed, and retrofitted. A smart building is the integration of building, technology, and energy systems. These systems may include building automation, life safety, telecommunications, user systems, and facility management systems. Smart buildings recognize and reflect the technological advancements and convergence of building systems, the common elements of the systems, and the additional functionality that integrated systems provide. Smart buildings provide actionable information about a building or space within a building to allow the building owner or occupant to manage the building. Flexible technology tools can bring together BIM models, data, and operational systems, integrating with facility data management systems. These environments provide a single source of truth with support for open standards, such as COBie. For organizations that will maintain legacy facilities in existing 2D, laser scanning can be used to collect a 3D representation of the facility, thus providing the ability to track assets in all locations. There are added advantages to having the 3D data, such as using the point cloud for safety briefings for contractors and repairmen. The traditional X's and O's on a whiteboard can be replaced by a digital walkthrough. Product documentation, such as submittals, data sheet, warranty, and specifications, are attached to assets, systems, locations, and facilities. The BIM model will associate location and provide visualization. Visualization of assets in 3D can be used to track mechanical, electrical, plumbing systems and identify areas of concern such as plumbing leaks. 3D visualization improves the overall coordination of systems, saving time and money. Building automation systems such as energy optimization, security, and fire protection can be integrated with BIM, providing the system's data in a 3D visualization format. COBie was developed by a number of U.S. public agencies to improve the handover process of building owners and operators. The primary goal is to ensure that owners receive the information about the facility in as complete and as useful a form as possible. COBie is a non-proprietary format based on a multiple-page spreadsheet which can be integrated with the 3D model for visualization and collaboration. If utilized to its maximum capabilities, BIM can produce value throughout the life of the facility. If the maintenance staff needs to access manufacturer's data on equipment, how many steps does it take? 5, 10, or more? There can be great savings on staff time if not having to take a half day looking for documents. A simple task, such as changing a light bulb, can be simplified if the maintenance staff knows exactly the bulb type and the manufacturer that needs to be replaced. All of the building elements can be identified with their associated documentation, such as warranty and maintenance log, in a single source. This will allow for more accuracy in maintenance planning, asset management, and provide the data to generate capital improvement budgets. While big data is a phrase most commonly associated with the finance and retail sectors, it has finally come home to roost in AEC, especially with the large amounts of highly trustworthy information using building information modeling technology and related systems. Using big data analytics to drive down the number of mistakes made in the real world, in everything from asset design to operations and maintenance, is key. It's far cheaper to get it wrong virtually than in reality. The phrase, "if only," should disappear from the lexicon of project planning, design, and delivery. The productivity boost alone will be a boon. PMC has 35 years of experience as a leader and innovator in digital engineering solutions for facility design and optimization throughout the life cycle of a project. From concept to commissioning, let our team of experts show you the answers to your challenges.